Hello everyone, I'm Andrea Valenza, and together with Luca Demetrio, today we will present WAF-A-MoLE, evading web application firewalls through adversarial machine learning. The main contribution of our work is WAF-A-MoLE, which is a tool to produce adversarial examples against web application firewalls. Then we have the state-of-the-art machine learning-based WAFs, and we have a benchmark and a bypass on those. And as a byproduct of our technique, we have a dataset of benign and malicious SQL queries, which we made available to the public. Okay, first of all, we need to talk a little about SQL injections. So what's a SQL injection? SQL injection is mainly being able to inject arbitrary behavior in queries, in SQL queries. And it's been the first risk of the OWASP top 10 since 2010. So what's the problem with SQL injections? SQL injections are usually sanitized, but there are many issues on that. We have state-of-the-art sanitization techniques for that, but sometimes a user simply isn't aware of those measures and the impact that a SQL injection can have on his website. Also, we have time constraints during the development process, and so sometimes companies can have a hard time sanitizing everything. And of course, we also have the problem of system administrators that have to run third-party code, and they are unable to modify it. So on the right, we see a SQL injection. This is a normal query, and we should provide the username here. But as we see, an attacker provided a SQL injection payload, and he provided, instead of running simple admin, he ran admin, and then we have these characters, which effectively modified the query. So this bypasses the whole password check, and this just selects everything. So we actively modified the behavior of the intended query. Okay, so web application firewalls are really useful in this instance because we can use it as a black box tool to inspect incoming payloads in our system, and we can detect and of course block attacks. So mainly web application firewalls are signature based, in which they have a whitelist or a blacklist of possible payloads, and we also have regular expressions to generalize those. But of course, the problem with web application firewalls is that they treat the symptoms and not the disease itself. So while web application firewalls try to block incoming attacks, they do not deal with real vulnerabilities. So the vulnerabilities are still there, and an attacker could try to bypass the WAF and still evade and still exploit the vulnerability. So another instance of web application firewalls is machine learning based web application firewalls. So the advantages are that web application firewalls based on machine learning are able to create a model which is based on the syntax of standard attacks, and we can train that on standard attack frameworks like OWASP ZAP or SQL map. Instead of using exact matching rules as the signature-based ones, we have a metric of proximity in which an attack is classified as malicious or not on a spectrum, and then we have a threshold to decide on which side the attack falls. So they have this spectrum is also referred to as confidence score. We have the confidence of the input payload, which is given by the WAF. We mainly deal with these three categories of WAFs. We have WAF brain, which is an end-to-end recurrent neural network. Then we have token-based detectors, and then we have a graph-based algorithm called SQLi GOT. And we have the references here on the bottom for all these tools. So we also try to retrain, because sometimes we didn't find the trained model, and we had to retrain them on our dataset, and retrain those and benchmarked them against a signature-based WAF, which is mod security with core set rules. So are these ML-based WAFs effective? Yes, mainly they are. They have high accuracy scores, and they perform quite well also against signature-based web application firewalls. But we also have a problem here. So the accuracy is never perfect. And the problem with not having perfect accuracy means that we have blind spots in the training process and in the model. So sometimes the model is not right in detecting an incoming attack, and they misclassify them. So we have this issue. An attacker could try to modify the incoming payload like this. This is an extreme example, but not as extreme. This is one of the payloads we generated with our tool. And we see that this one is the same attack. It carries the same meaning as the attack on the left, but the attack on the right is more complex, and it's more likely to not be recognized by the tool, by our WAF. And this leads to adversarial machine learning, which I'll leave to Luca Demetrio to talk about.
So, hi everyone, I'm Luca, I'm the other author of this work, and I'm gonna follow with the presentation. And as Andrea already told you, an attacker might want to take a payload and modify it, altering it to fly under the radar of the target WAF. And this basically falls in the area of the adversarial machine learning, where we introduce the presence of an aware adversary whose aim is to exploit some blind spots that are present in our model, or in general in our victim model. And we are going to focus on evasion attacks. And an evasion attack is, I take a malicious payload and I modify it, and now it is seen as legit from the WAF, but it is not. So the malicious content is still present, since all the manipulations we have added to the payload are only syntactical and they preserve the malicious semantics. So this can be posed an optimization problem, where here we have F, which is the WAF, which attributes a confidence. C is the class, where in this case the benign class, and we want to minimize the distance expressed as D between the confidence from the class computed by the WAF and the target class. So C of X is the set of constraints we need to impose on X to not let it lose the malicious semantics. To do this, we developed WAF-A-MoLE, which is basically a gray box tool. It takes in input a WAF, and it computes adversarial examples for that WAF, and it doesn't need to know any details of the target WAF. It just needs the score computed from the WAF. It's efficient because at every round of generations of new malicious payloads, it only keeps the most promising one, and we're gonna see how WAF-A-MoLE does that. And it's really plug and play. So you code a proper driver for your WAF, and then you can plug WAF-A-MoLE to this driver, and you can just run WAF-A-MoLE to find new adversarial examples. So here there is a picture showing the overall architecture of our tool. So we have a priority queue, then that holds all the mutation. We draw a mutation, a mutated payload P, and we put it into a fuzzer. The fuzzer generates more payloads, and then it throws to the model. The model compute V, which is a confidence score, and we put together with the payload again in the priority queue. And we keep repeating this process. So this is our mutational fuzzing engine, which is the main part of WAF-A-MoLE, and it basically say what I've already told you about the picture. And here we can really appreciate that while V is strictly higher than T, so I don't have found any real adversarial example, I iterate the mutation part, taking the most promising payload from the queue, then I classify it and I put it back in the queue until evasion. So the priority queue ensures that the fittest candidate are due before all the others for the mutation, during the mutation. So, but how WAF-A-MoLE mutates our payloads? So we have listed 1, 2, 3, 4, 5, 6, 7 different operational mutation that basically alters only the syntactic of a payload. For instance, we have the case swapping, which is I just flip from the case of a letter, then I can substitute the white space with a comment, then I can inject some comment inside a multi-line comment, I can rewrite the content of a comment, and I can encode an integer to another encoding like in another base. I can swap operators, like removing an equals and putting a like, and then I can insert some logic invariant operators like 1 is equal to 1 or 2 is not equal to 3. So we take all of these operators and we just let WAF-A-MoLE explore the space. Here we have a representation of a run of our tool. So this tree doesn't really exist. It's just a structure that is created during the process by the priority queue itself, because we save which mutation has been created by who. So we start from our famous admin or 1 equals 1 payload, which is 100% sure it is malicious. Then we apply a simple mutation that adds, for instance, a comment, any score decreases, then we have a bunch of other choices, and we keep going. So imagine that we arrive here, so after applying another mutation, and we are stuck here at 86%, and we can just dig more. Then thanks to the priority queue, we can just take another candidate, which is, for instance, this one, and we can continue the process. And here we can say that maybe this was fittest than the other one. So which are the results? On the x-axis of every plot, we put the number of mutations that are applied to a single payload, so it is incremental. So starting from 0, which is the admin or admin apex 1 equal 1 payload, to I don't know what does it mean anymore. And we basically tested WAF-A-MoLE with a random approach, because WAF-A-MoLE is guided, but we want to understand if the underlying WAF is smart enough to endure random mutation, and in fact they were not, at least not all of them. 5 of them, so the recurrent neural network and the token-based classifier, were all weak to the random mutations. So this implies that the model that didn't really learn what does it mean to be a SQL injection, just starting from the syntax. While other classifier, the SQLi got variants, were more robust to some extent, but still they are vulnerable. So at some point they all fall under the detection thresholds. So these are the plot by varying the number of mutations. Same plot, but from a time perspective. So since this is a fuzzer, it's a smarter fuzzer, let's say. Since this is a fuzzer, we are really interested in understanding how much does it take to produce an adversarial example from a starting point. So on the x-axis, there is the time in seconds on a log scale, and we can see that, for instance, for many of them, we are under 1/10 of a second to reach the evasion. and while other, like this again the SQLi got, were slower to compute an adversarial payload. This is mainly due to the fact that SQLi got has a more complex feature extraction phase with respect to the other. So this is why SQLi got really took a lot of time to be evaded. But still, evasion was successful. To conclude, we can say that the attacker possesses an infinite amount of ways to represent the same malicious payload, and the victim WAFs can't hold so many possibilities. So some of them they're gonna for sure fall into a valley of zero probability of being a SQLi. And again, the complexity of the feature extraction phase doesn't imply necessary adversarial robustness. So you might have very complex information taken from your data, but this is not gonna defend you from finding blind spots. So the complexity of the information is not strictly correlated to the ability to generalize over noise. And again, since these are statistical approaches, they might not be effective against an adversary that knows how to shift the confidence of a particular sample to point A to point B, namely to being malicious to be a legit query. And unexpectedly, our random fuzzing technique is able to bust some of the classifier we've used for this work, and this was kinda strange for us, since we believe that at least the random attack wasn't that successful against that model. And for the models that were robust to such noise, the WAF-A-MoLE, so the guided approach, was incredibly successful. With this, we conclude our presentation. We really thank you for your attention, and these are the links to the tool, so to the GitHub code. And here there is the dataset we use for training the models. And here below you have our mail and our Twitter accounts. So if you have any question, just send a text or drop a mail to us. So thank you for the attention.